This is the brief on ultra-supercritical power technology. By pushing water way past its physical limits, using extreme heat and pressure, power plants are dramatically boosting efficiency and slashing emissions. It's an absolute engineering marvel. Imagine bypassing the boiling water on your stove entirely, instantly creating a superpowered, homogeneous fluid. So, how do we pull this off, and why does it matter? First, let's look at the thermodynamic leap. Older plants max out near 38% efficiency, but ultra-supercritical plants, they crank the pressure to over 325 times our normal atmosphere, blasting past 700 degrees Celsius. At that extreme thermodynamic critical point, water just skips boiling altogether. So, what happens when water literally forgets how to boil? Second, we get a massive efficiency and environmental payoff. These plants hit an incredible 46 to 48% net efficiency. By burning significantly less coal per megawatt hour, they drop CO2 emissions by 11% while naturally reducing nasty pollutants like nitrogen and sulfur oxides. I mean, while we transition to renewables, isn't squeezing every drop of efficiency out of existing fuels a mandatory stopgap? But that begs the question, how do the actual pipes and boilers not melt under 700 degrees heat? Finally, we have the hardware and material innovations. To survive these brutal environments, plants use advanced nickel-based alloys and high chromium steels. It's kind of like swapping a standard cast iron skillet for heat-resistant space shuttle tiles. They also use a streamlined once-through boiler design, letting the plant ramp power up or down incredibly fast to perfectly match grid demand. Ultimately, ultra-supercritical technology relies on extreme thermodynamics and space-age metals to squeeze maximum energy from fuel with a smaller environmental footprint.
On modernizing lignite coal power. Lignite, or brown coal, is notoriously wet and inefficient, but new drying and combustion technologies are revamping how we burn it to boost efficiency and cut emissions. Honestly, burning raw lignite is kind of like trying to light a soaking wet sponge on fire. First, breaking the moisture barrier. Before we burn it, we've got to wring out the sponge. Raw lignite is up to 70% water. We dry it using WTA fluidized bed drying, using internal waste heat to drop moisture to 12% and boost efficiency by 4%, or mechanical thermal extraction, using heat and pressure to literally squeeze out the moisture. The bottom line? Drying it leads to a massive 18% reduction in CO2 emissions. Second, advanced combustion and heat recovery. With dry fuel, how do we get the absolute most out of it? Well, modern plants capture waste heat from flue gases, recovering 80 megajoules per second to add almost a full percent to total efficiency. Plus, they use low NOx burners to control primary emissions, entirely skipping incredibly expensive SCR scrubber systems. These optimized plants can hit over 43% net efficiency, rivaling high-grade hard coal. Finally, the bottom line numbers. Let's look at the scoreboard. Existing subcritical plants sit at a dismal 28% efficiency, pumping out 1,250 kilograms of CO2 per megawatt hour. But upgrading to a new supercritical plant with dried lignite, efficiency rockets to 41% and CO2 plummets to 820 kilograms. So, are we making a dirty fuel perfectly clean? No, but we're making a massive, measurable dent in its carbon footprint. By squeezing the water out and optimizing the burn, we're extracting maximum power and significantly fewer emissions from one of our most challenging fuels.
This is the brief on supercritical coal power. By pushing water past its extreme physical limits, power plants are unlocking unprecedented efficiency, proving that even a legacy fuel like coal can be upgraded with high-tech physics. First, it all comes down to hitting the critical point, which is 22.1 megapascals of pressure and 374 degrees Celsius. You're basically squeezing and heating water so intensely that it essentially forgets whether it's a liquid or a gas, right? It just merges into a supercritical fluid. Older, subcritical plants operate below this threshold, stuck at kind of 34 to 38% efficiency. But supercritical and ultra-supercritical plants, they completely blast past the 45% mark. Second, this massive efficiency boost creates two distinct real-world advantages. Burning less coal per kilowatt hour directly reduces CO2, SO2, and NO2 emissions. Now you might ask, sure, it's a bit cleaner, but aren't massive coal plants too clunky for today's fast-changing power grid? Well, actually, once-through boiler designs allow these plants to rapidly ramp their output up or down to meet fluctuating grid demand. Finally, who's actually putting this into practice? China's Weiguoxiao Phase 3 leads the pack with a record-breaking net efficiency of around 48.5%. Over in Germany, RDK8 achieves over 47%, which is among the absolute highest for hard coal. And the USA's first ultra-supercritical plant is the John W. Turk Jr. So, supercritical technology uses extreme physics to squeeze more energy and flexibility out of coal while lowering its environmental footprint. Extreme engineering is literally reshaping the baseline of global power.
This is the brief on the coal paradox. Today, we're diving into new data showing why so-called high-efficiency coal plants are actually a dangerous illusion, fundamentally threatening our 2050 global decarbonization targets. First, let's talk about the trap of HELE technology. That's high-efficiency, low emissions. You know, older subcritical coal plants pump out over 800 grams of CO2 per kilowatt hour. The absolute most advanced plants hit 50% efficiency, but guess what? They still spit out a massive 670 grams. Compare that to wind and solar, which sit beautifully at a perfect 0. High-efficiency coal is literally like smoking a cigarette with a slightly better filter. It's still totally toxic and miles away from simply quitting. Second, because of that leftover toxicity, we absolutely got to talk about the only real technological fix, carbon capture and storage, or CCS. Only CCS can drag those emissions below the critical 100-gram threshold needed to stabilize our climate. So, if the IPCC says we need near-zero emissions by 2050, why are we celebrating a 50% efficiency rate when we literally must have carbon capture to survive? Finally, let's look at the terrifying reality of our current infrastructure plans. There's a whopping 1,400 gigawatts of planned coal capacity right now, even built super efficiently. These young plants have 50-year lifespans. That creates an unavoidable lock-in risk of 175 gigatons of CO2, making a 2-degree climate pathway completely impossible. We absolutely cannot accept this. Building a young coal plant today is essentially building a 50-year climate time bomb that completely ignores our 2050 deadline. Upgrading coal plants without actually capturing the carbon isn't a climate solution. It's just a highly efficient roadblock to our survival.